the loadings on the structures are the loads on the structures can carry the loads imposed on them and transfer, of course, successfully the loads to the foundation. And you can see now that it's raining, there's a lot of issues with collapsed buildings. If I were to make a wild guess, not a wild guess, an indicated guess, probably does have something to do with foundation, because the soil, the strength of soil is okay. First, this is your if this is the foundation, this is the column, and we are concerned that the load here this load. So this is the bearing capacity. Remember we talked about the bearing capacity. Okay, let's call it Q. So we are saying this sigma should be the sigma, of course, the sigma, which is the P over A. So Q, this is the Q. So if this is the A, the area is A, then this is QU, then P over A should be less than QU, the imposed load. But of course we know that C, the effective stress of the soil is equal to C minus the pore pressure. Now rain, of course rain will increase the pore water pressure. Once the rain increases the pore water pressure, you can see this value. If this value goes up, what happens to this, to the effective stress? Classroom? Hello? Come up again, sir. You can see what I'm writing on the screen, right? Yes. So if the excess pore water pressure increases, what happens to the effective stress? Hello? You can see the first. Yes, so it gets low. So that's the issue. So you can see now there is a lot of already. I think 2 or 3 buildings have collapsed in Nairobi since the onset of rains. So this is the issue. Okay, of course maybe they will investigate and tell us if they will do that. But most likely it can be guessed that this is a geotechnical engineering problem. So this is the reason why at the stage that the design, of course there should be site investigations, and then you write a report and you determine the appropriate values. You remember the values we are talking about, C and phi. So this is important, C and phi. In fact, to preempt, the values of the bearing capacity can be calculated from so Q calculated from value C and C. I don't worry about the, okay, so value C and C plus Q and Q and Q and Q plus half B gamma and gamma. So I need you to at least picture this. So this C, these values, this is the C that, this is the C from this formula. Tau equals, no, that's not right. Tau cannot have a prime, so tau is just tau. Shear strength is just shear strength. So shear strength is plus sigma tan phi. So this C is C there, and these values N, Q depend on phi. N C, so SC and Q and N gamma depends on phi. Those values depend on phi. Of course, this gamma is the unit weight and B is the width of the foundation. So you can see how these things are tied together. So the C and the, so then if there is water, then it will affect the values, this effective stress, because like we said that the sigma equals sigma prime equals sigma minus U. So if this value goes down, you can see the shear strength of the soil also goes down. If this value goes down, you can see the shear strength is also going down. So if someone tasks you to explain why probably the onset of rain, a lot of buildings collapse, you can see it's tying together that the excess water pressure reduces the effective stress, and you can see if this value in the formula, if this value goes down, if this value reduces, then you can see the effective, because the strength of the soil, of course, is governed by this formula. So this is the key idea. So although today we have finite element method which can combine elastic and plastic components of soil response to loading, the use of lower and upper bound plasticity is important in enhancing our understanding of plasticity in soil. Many of the methods we use in the technical design. This is an overview of both lower and upper bound solutions to classic bearing capacity problems. And much of this presentation is we are relying on reference, but the questions we checked the questions based on the. Okay, this one is also from another reference. So this is from the work of this guy with the and so lower bound theorem, the truth is higher corresponding to Theorems system. Okay, we are going to talk about this in detail. So we are saying that because you can now see why I said that we apply a higher factor of safety to bearing capacity between 2.5. In fact, for design of foundations, we always even apply a higher bearing capacity and a higher factor of safety. In fact, usually between 3 to 6. Depending on the degree of uncertainty, the higher the degree of uncertainty, the higher the factor of safety. So initially we said 2.5 to 3, but in fact in reality we apply 3 to 6 for actual design out in the field. Because the methods of determination there are some levels of uncertainty. So you can see here we're saying the true failure load is in fact higher, larger than the load corresponding to an equilibrium system. So because in theory we like simple things, we like to assume an worst stress state scenario and take equilibrium, and at the limit we try to compute load that would possibly cause failure or collapse. But in fact here the lower band theorem says that load that we are computing at equilibrium, in fact the true failure load might be higher, is higher than the actual failure load. So that means the assumption we are making is underestimating the actual strength of bearing capacity. So but on theorems the true failure is actually small load corresponding to a mechanism if that load is determined in virtual principle. Elastic perfectly plastic type of soil model, the lower bound solution is where the stress at some point reaches the elastic limit, while the upper bound solution has the stress fully plastic to the boundaries of the system, at which point the capacity of the system to resist further stress has been exhausted or reached its upper limit. So this is just to show you that in fact in reality the boundary it's difficult to determine the bearing capacity with certainty, and so this to circumvent or to solve the issue there is a proposition of some lower limit and some upper limit bounds, so we will be sure that our bearing capacity lies in between somewhere there. So you can see the lower bound says that the true failure load is higher than the equilibrium state. The upper bound theorem says that the true failure load is higher than the load corresponding to a mechanism if that load is determined using virtual arc principle. Since you are assuming an elastic, perfectly plastic type of soil, the lower bound solution is where the stress so at some point reaches the elastic limit. So while the upper bound solution has the stress fully plastic to the boundaries of the stress at which point the capacity of the system to resist further load is exhausted. Okay, simply put, if this is your foundation, if this is your foundation, so there would be this here, and this would try to fill in a log spiral way, and this is surface. Okay. Okay, let's see here. I think there's a diagram. There's no diagram. I think there should be some. in fact, actually, yeah, we are going to have some explanation. So anyway, so here, what we are saying, normally, this is the foundation, and this is the ground level. So the idea is that this foundation will force a wedge or face through a wedge and a spiral, and of course sometimes causes heave there. So these ones are heave. So now the issue here is that first is what you call local shear failure, because this thing this can fail in two ways. We have what is called local shear failure, and general shear failure. General shear failure. So you need to consider different things. So for example, we are talking about loose sand, and soft clay, one of these areas will so some localized region a few patches here will reach elastic limit. Yeah. So some of the soil here will yield, not the entire structure of the soil will fail, but some local areas here will fail. So and this is usually associated with loose sand and soft clay. So that's what we call local shear failure. But for stiff clay and dense sand, then we have the general shear failure. So for this one, all these at the boundary here, the stress will yield, let's say, and everything here will reach a plastic limit at the boundary. But for the local shear failure, just a few portions under the foundation will fail. That's why we call it local shear failure and general shear failure. So there are two things. Local shear failure is associated with loose sand and soft clay. General shear failure is associated with stiff clay and dense sand. So when there is local shear failure, we have the lower bound solution, and when there is general shear failure, we have upper bound solution for the bearing capacity. So for the assumptions, one, we are seeing that the foundations are rigid to the soil for upper bound and flexible relatively to soil in lower bound. With the latter, a rigid foundation produces infinite stresses at the edges, which means the lower bound solution is zero pressure in that case. So of course we are making very reasonable assumptions. Of course, if you compare a foundation which is made of concrete to soil, of course the concrete is more rigid compared to the soil. So we are very clearly saying foundation is very rigid relative to the soil. So for upper bound, and flexible related to the soil for the lower bound. With the latter, a rigid foundation produces infinite stress. So in the lower bound case, the rigid foundation is assumed to produce infinite stresses at the edges, which means the lower bound solution zero pressure at the edges in that case. So number 2, no sliding occurs between foundation and the soil. So the foundation is rough. So the coefficient of friction here between the soil and the there is some roughness, so that so this edge here is rough, so that there is some friction between the soil and the foundation. So that's the point. So applied compressives and applied vertically. We apply load is applied compressive, so we apply a compressive vertical load, and of course is applied at the centroid of the foundation, that's the upper bound, and uniformly on the lower bound. No applied moments present, so there are no moments. We are only applying a load at the center, concentrated load at the center. So you can see here, as this is kind of a point load vertically at the center. So for the upper bound, we are talking about the point load, and for the lower bound, we are talking about a uniformly distributed load. There are no moments in the solution, and foundation in a strip footing is of infinite length. We usually use per meter length. Now that assumption says that this so this is the scale x z. So the length in the z direction is infinite, is long. So you will see the definition of strip foundations. We are saying the ratio of the length to the width is very high. So if you consider the length to the width, that value is very high. L to B is very high. So that's what a strip foundation is. So that's why we are saying the length is kind of infinite. So I need you to think of something like the boundary wall, for example. If you compare the width is almost 200 millimeters, right? And if you check the length, it spans over the entire length of the property. So let me say, for example, the property 100 they measure in feet. So 100 feet is how much? Is times 0.3 is about 30 feet. So if the length is spanning over 30 meters, so let's say that's 30 meters, 30, and the width is 0.02 200 millimeters, 0.02. You can see that's about 1500. So then you can say this is the idea, in fact, that the ratio of the length to the width is infinite for strip footing. Soil beneath the foundation is homogeneous semi-infinite mass. For the derivations here, we additionally assume that the properties of the soil above the base of the foundation are same as those below it. So basically we are saying that soil is kind of some. Now the C5 here and gamma is the same as C5 here, so this is below the foundation. C5 and gamma are below the foundation. That's a point. And then we say the Coulomb failure criteria applies for the soil. So therefore, the shear strength of the soil is defined as the shear strength of the soil is defined as C plus sigma sigma and phi. So this is the Coulomb failure criterion that is applicable, but no consolidation occurs. You remember from the first topic we said the difference between consolidation and compaction. Compaction is densification of soil by removing air, and we remove air by using loads and some vibration action. Consolidation is densification, yes, but by removing water specifically, and of course water is removed by such as the vibration actions cannot affect water. So consolidation is basically densification by removing water. Soil above the bottom or the foundation has no shear strength, is only surcharge load against the overturning. Yeah, so something interesting as well. So here the soil above the foundation. So here the shear strength of this soil is 0, but only acts with this. So the only function of this soil here is that it has surcharge. It provides. So if you want the stress there would be Z gamma, but the shear strength of that soil is 0. That's what we say. So only the shear strength of the soil here is applicable. So in other words, we are ignoring the shear strength of the soil on top, but assuming that they apply surcharge. That's a very conservative assumption, so that you are ending up with a safer design, because in fact the soil above of course will have some shear strength, but it's a conservative assumption. We are simply ignoring the shear strength of the soil above the foundation, but also using the surcharge of the soil above the foundation to our advantage. And then the effective stress of the weight of soil act in a hydrostatic fashion. So we are saying that the hydrostatic stress rate, so the stress here, the stress so it's a vertical, is the same as the horizontal stresses. So this is what you are saying. So sigma V and sigma H. Of course, you know this assumption is not correct. Of course, it's not the real situation, because you know that the assumption. But of course, you know in soil there is a ratio between sigma H to sigma V. But we know how to do it when there is the active case and the passive case and the at-rest case. But you see, soil is something that is not only affected. So in the at-rest condition, there are no effects. In passive condition, that means you have made an excavation. One side is passive and the other side is active. In other cases, this ratio is affected by many other things. So not necessarily the factors that we talked about. So in a such a case where there is a foundation, there's a foundation, so the foundation is adding its pressure there. There's also the burden. So the assumption here is that the sigma V and sigma H are the same. But you can see there are several factors that are affecting this distribution, and such that the passive and the active conditions are the assumptions of the at rest, passive and active conditions are no longer valid. So the assumption here when you're deriving this formula is that the horizontal and the vertical stresses are the same. I think this is repeated, so we need to delete it. So these are fairly standard assumptions for basic bearing capacity theory. The additions from these are workarounds that have been developed that include the analysis of finite foundations, squares, and rectangles, circles, etc. So the theory of elasticity of infinite step footings. Let us begin by considering the system below of a step footing with a uniformly distributed load. The variables are defined. So we'll follow this slowly. I'll try my best to explain. So as if, of course, if you have a step footing like a wall, so this is the thickness of the wall and there's some load. So of course you expect these are stones being arranged there in some way like this. So of course they are going to apply some uniform load on the soil. So that's the idea. And we are seeing the width is delta, as we have said, and of course the center width here is Z. So based on some reference points, so some depth below the foundation, right? We are always concerned by the stresses in the vertical, horizontal, and the Z direction. So if this is a sigma Z, sigma Y is in this direction, and so sigma Z is up. I think sigma Y is in this direction, and sigma. And so that's all. And then we define this angles. You can see angle beta, angle alpha, and so this is alpha over 2. The bisection of this angle alpha, we get alpha by 2. So if we define this kind of scenario such that beta, angle beta is alpha over 2 plus beta prime. So angle beta is this angle here. So it can be shown that we are not getting into the mathematics of how to end up here. So probably you need the point rather than the mathematical manipulation. So we can prove that sigma Z can be calculated as shown. Of course, this is basically based on the theory of elasticity and also based on some trigonometric relationships of the trigonometric relationships of this triangle, and also of course the theory of elasticity. And sigma y, so sigma z, we interpret sigma z and sigma y, you can see that. And also of course the shear strength is also important. So it can be shown that the principal axis of the stresses at the point are along a line in the middle of angle alpha. This is the dashed line. So the principal so this is the direction of the principal stresses. Remember the direction of principal stresses we said remind you. Of course, we assumed, I told you that this okay, mostly they are assumed to be vertical. So sigma, this is sigma y. Okay, let's say sigma 3, sigma 1, sigma 1, and sigma 2. 90 degrees to each other. So we are saying here again, so you can see this is the direction of the sigma, one of the principal stresses, that means the others will be here at 90 degrees, and another one to do this one. So if this is sigma 1, sigma 3, and that's sigma 2. So anyway, that's what you need to understand is that the principal axis is here based on that arrangement. This is the dashed line in the above diagram. Along this dashed line, the beta is 0, and thus alpha over 2 is negative beta. Alright, beta prime. The principal stresses will the load become. So based on what we've said, what happens? The principal stresses I think this is some issue here. So wrong. Let's see. Let me take just a minute. So and then now we go into the details of the actual layer bond. theorems. So as shallow foundations are seldom built with base of the foundation at the same elevation as the ground line, they are customarily built to a depth from the foundation as shown. So we rarely put the foundation on the ground level. That's the point. It's very rare. Of course, the foundations have to be at least sunk to some depth into the ground. Of course, because the overburden also adds to the overburden stress from the surcharge is useful. So at this point, for the purpose of analysis, we transform the effect of the depth into overburden stress. I think we mentioned this before, which is the product of the unit weight of the soil gamma and the depth of foundation base from the surface D or H as shown. So the key is just gamma times H. We already said this. So the width is B, and so the key is gamma times H. So this is a better representation of what we are saying. So this is B1 and B1. So this is the midpoint. Basically, I think that should be self-explanatory. So the effective stress at any point below the surface is given by sigma naught is gamma, of course gamma times height, and at the point Z. So anywhere, if this is height, this is height, this is height H, then the effective length, effective, so somewhere there, so this is Z, then the sigma naught would be H into gamma, so if this is Z, some height there Z, additional height Z, sigma naught is gamma into H plus Z. You should know this, the gamma into H plus Z from the principles we have already established before. So now, at the point the hydrostatic stress assumption becomes important. So remember the hydrostatic stress assumption. So in any case, so this is the reason. So at that point, then we are saying at any point, so sigma naught, and this is also sigma naught. Okay, so that's the issue. That's the point. So becomes important the transformation from equation 1 to 3 and 4 to 5 involve an axis rotation. Assuming the soil act hydrostatically means that no matter how we rotate the axis, the addition of effective stress to the principal stress is independent of the direction. Doing just that yields the following equation. So how we transformed equation 1 to equation 3 is just axis rotation. We already said this is just axis rotation, and then equation 4 to 5, 1 to 3, and then equation 4 to 5 involves axis rotation. Now, assuming the soil acts hydrostatically, that means the pressure is the same, the horizontal and vertical are the same, means that no matter how we rotate the axis, the addition of effective stress to the principal stress is independent of direction. So if we add effective stresses, then it doesn't matter the direction. So here you can see now this is the original equation of equation 1 or equation 4. Yeah, equation 4. And this is the original equation 5. So we are adding effective stress to both the equation 4 and 5. So that gives us equation 7 and 8. So at this point we state the Fourier-Coulomb theory, which you already know, and can be restated as shown. So now if you substitute equation 7 and 8, so this is equation 7 and 8. This is still the Mohr-Sacco, the expanded Mohr-Sacco. We go back and we talk about the theory is something like this. The Mohr-Sacco basically. So now if we substitute this, because we have sigma 1 and sigma 3, in this equation, which we have here. Then we substitute equation 7 and 8 in this long equation for you, and we are interested in solving for z. If we solve for z, this is the solution for z. Alright. You need to get the procedure, the theory, but the formulas maybe. Okay, you need to have an idea of what the formulas are at the point. So if you solve for z, this is the solution, a very lengthy solution nonetheless. So at this point we want to find the maximum value of z at which a point of plasticity first sets in. We do this by taking derivative of z relative to alpha, and setting it to 0. So why we are doing this is we want to involve calculus or integration, not what is called taking derivative is differentiation. So because when we get into differential calculus, it's easy to solve some of these things. But however, in this section, just see what we are doing and how we get to the lower bound theory. Don't worry, lower and upper bound theory. Don't worry too much about the formulas. So we do this. So this is the equation, right? So we want to find the minimum value derivative of z. So you take dz. You take dz, the alpha, d this equation, the alpha down there. So that's what we are doing there. And then we set that to equal to 0. So when you differentiate that equation, this is what you get. Okay. So it can be excuse me. It can be shown that this condition is fulfilled when alpha is pi over 2. So basically you can see what we are doing. We want the point, so we are pointed that that's the point when pi is alpha over 2. This is 45 degrees. 45, pi is 90. No, pi is 180, is it? 180. So pi over 2 should be 90. So it can be shown that this condition is fulfilled when alpha. So this condition here is fulfilled when alpha is pi over 2. That means that is the solution. So we substitute back in the equation 11 gives a value. So the value we solve from this derivation, we substitute back here, and remember the objective is to get the maximum z. at which onset of plasticity sets in. So if we substitute back in equation 11, we end up in equation 3. So it gives us the value of Z at which point of elasticity is first induced. So if we solve for pressure, remember we are interested in the stresses. If we solve for pressure P, the pressure will be in reality the critical pressure at which plasticity is first induced. For the pressure, so this is in fact the lower bound theory. That's all. So okay, I'll go back slowly and try to in the point, all I need is to see the point here. At this point we need to face reality and note that if the point we are looking for is the point at which plastic deformation begins, then it cannot be at any depth other than the base of the foundation. If Z max is 0, making the final substitution, then at last we have the lower bound solution. Okay, so the logic here first, without the formulas, so don't worry so much about the formula. So first we establish the stress state about some point, some angle, if we are making an assumption of steep footing. That's the first thing. 2, we are interested in sigma Z and sigma Y, the vertical, remember the vertical, because by default we already are seeing that the sigma Z and sigma Y, these are the principal stresses. You remember the principal stresses, the maximum stresses, and of course we are interested in the principal stresses and also the shear stress. Remember this, so sigma Z and sigma Y. We can show that the principal axis in fact lies here, right, at the midpoint of the at angle. So at this point the beta, this beta, this angle we are saying is 0 in fact, because on this line, this angle, the beta prime is not there. So that's what you're seeing, the beta, not beta prime, but beta is 0, and thus alpha over 2 is negative beta prime, and the principal stresses due to the load. So once we know, you can see here we're using beta is 0, right? Beta here is 0. So if we substitute in this equation, so basically cos beta, if you substitute beta here, cos 0 is 1, so this part is lost, and sin beta is 0, is it? Okay, so when you substitute beta is, you substitute in this equation, then you transform them to sigma 1. So actually yes, so you can see, logic, if you remember logic, logic is still consistent with common sense. You remember we said that, class rep, are you still with me? Please confirm that you're still with me. I hope I do not want to lose you. Class rep.
Yes, we are okay.
So now we said here that this is sigma 1, sigma 3, and sigma 2. But on this axis, the shear stresses are how much? Anyone who remember? On the principal planes, principal axis, what is the value of the shear stress? Hello? Hello? Class rep. said the value of shear stress on the principal planes is how much? You can't even you can see here, if you substitute beta is 0, this part is not there, but this is 0. So it means the shear strength is how much? I'm literally giving it away to you people. Hello? Hello?
I'm getting a 0, sir.
Yes, it is 0, of course. Yes, it's 0. And you can see, so on this is a principle that you already know, you should know. I said, on the principal planes, the shear stress is 0. That's it. And that's common sense. And it makes sense because you can see here, you substitute this one disappears, this one disappears, and this one becomes 0, which is true because on the principal plane. So therefore this becomes I think this becomes sigma 1, and this becomes sigma 3, and this reduces to nothing because on the principal planes the shear stress in fact is 0. That's the point. So I said this one becomes sigma 1, and this becomes sigma 3. This will become minus. Okay, this is, you remember, alpha over 2, so this becomes there is a minus that comes, sorry, there's a minus that appears here. So common sense still is kept. So and then because of the additional overburden stress, which is gamma times the z is h plus 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 the height, but this is additional, so we are seeing some hypothetical. So this is below the foundation. So this is if the foundation, okay, so the foundation is here and this is how it is h, and we are talking about some theoretical point here where there is an additional value z. Alright, so not for the foundation. So there is just gamma into h plus z. Alright, so then if the assumption of the hydrostatic stress is state, we add the sigmas, these additional stresses into all the stresses. It doesn't matter the orientation because of the hydrostatic. If pressure is increased in every direction, then it means in every direction they are increased uniformly. So sigma 1 and sigma 3 becomes those values. And also remember that sigma 1 and sigma 3 and at those with these values the shear stresses disappears to 0. Then if you substitute this in the Coulomb theory, you substitute now these values here in the Coulomb failure criterion, and then so once you substitute the values here, then you try to find the value of z. This is z. So now here we are interested in making the alpha equals 0. That's the point. So when we differentiate this equation, this is what we get. Alright, and if we try to solve this equation, we get that alpha in fact is pi over 2. And if we substitute that pi over 2, because we are interested in the z, where we will get the onset of plastic yield, substitute the power over 2 here, then we get the Z max as 1. But also logic is important. So, and then from this Z max, we can calculate the P, and that is the lower bound, the load that we are looking for, in fact. So, but logic and common sense is still not, we don't ignore, because in fact, if you load, if this is your foundation, this is your burden, sorry, this is the burden. Now plastic deformation not here, based on logic, and here you know that Z max is 0, because that is the level of the foundation. That plasticity cannot start anywhere else apart from the position where the foundation is in contact with the soil. So having said that, then we substitute that logic into this formula that we already. So here, you know, where you see Z max, you put 0. So here Z max is 0. So that means that collapses this formula, and then the remaining part now, that is your lower bound solution. Remember, we are talking about the lower bound solution. So the logic is more important. Don't worry too much about the formulas. And so that's the lower bound solution. So for the upper bound solution, the upper bound solution is well known, one path in geotechnical engineering, and only the highlights will be shown here. In 1920, Pant and Reisner solved the problem for soil by neglecting its own weight equation. This, I think, 16, not 6. Equation 16. They determine the failure pattern and surface can be represented by the following configuration. They determine the upper bound, the critical pressure is given by the equation. So the upper bound solution here is ignored quite a bit, but I've said that you need to understand the logic more than the formulas itself. So the point here, here you need to understand what the upper bound and the lower bound is, the concept rather than the formula. So they determined, so that the upper bound critical pressure was determined by the equation shown. So for this is the assumed slip loss by Pant and Reisner. So if you define and Q, you remember, as I told you, eventually we will know that because we want the bearing capacity of the soil is C and C plus Q and Q plus, a good student, you better start remembering this formula, gamma B and gamma, and Q, this I told you is a function of phi. You can see now the actual variation. Okay, so now the critical value can be obtained based on equation 18. Based on equation 18, and NC, again I told you NC is a value of phi, based on a value of phi. So then we have the critical load is that So the only thing missing from the equation is the effect of the weight of the soil bearing on the failure surface at the bottom of the failure region, shown in figure 4, and thus the bearing capacity equation. So voila, this is what I was aiming at. I think I said this. So that's actually the bearing capacity of the soil. This is how to calculate the bearing capacity, CNC plus Q and Q. So please start by remembering this equation. Would be of service to be okay. However, you write B gamma. All these values and Q and gamma, you can see and C, you can see and Q, you can see and gamma are functions of phi. So don't worry about and Q and gamma. There are tables of how to determine them. So there's a table, a curve, it will always be provided if you need them. So this is why I was telling you not to worry too much about the formulas. Once you know what they mean and how to determine them, there are tables too where you can read off those values. So no need to worry too much about the formulation. All you need is to remember this formula, how to determine the bearing capacity. After that, once you remember this formula, the details of Q, okay, Q actually, Q is the overburden, Q is the overburden now, Q is the gamma times df, df is this, and please, you can stop me if you don't understand, that's why we are here. So that's the value of df. Okay, this is the value of df. So we should know. So this one can be gotten from a table, gotten from a table, based on phi. So you'll be told what phi is. You can read them from a table. This will be given. It could be 1820. This is the width. This is the dimension of the foundation, and Q is there. So you know everything. Don't say that you do not know how to determine that. So this last bearing capacity factor has been the major subject of. So actually, the people agree basically on these two. The NQ, there is no problem with that. The NC, there is no problem in that. But the N gamma is a lot of debate exactly how to determine the N gamma. So that's something we are going to talk about a little bit in detail, because Terzaghi also, these are formulas that were proposed and defined by Terzaghi, of course, from the work of Prant, but how to determine N gamma is a subject of debate, because various researchers find different values of N gamma. So it is a subject of variable solutions over the years. The one shown here is from VESIC. So there is VESIC, there is Prattle, and there is Terzaghi as well. So they agree on the two. The various researchers agree on NC. There is not a big difference from different researchers. But when it comes to N gamma, the values are really, there is some variation. So it's subject of big debate as to why that is so. So you need to understand all that. So here we are presenting work proposed by VESIC, but just so that you are aware, there is a debate. So here I don't even know how to. It's very simple, in fact. You are asked to determine the bearing capacity solution. Okay, because this is an assignment, so you can do the tedious work. So here you only need to know how to substitute in this value. Q equals CNC, and now here I want us to participate. CNC plus plus what? Anyone who remembers the formula? Because you know you find this in the exam. So please, how do you, I've said this equation several times in this class. So I need you people to now tell me Q equals what? And guide me how to solve this part. Q equals Christine. I told you to understand the logic rather than crime, so please. I also learned by participation. Christine? Hello? Hello?
Better.
Yes.
Hello, Doc.
Yes, I can hear you.
I think my network has a problem or what?
Yeah, I can hear you very well.
I had a problem with that formula because there are two formulas that look similar but they were different. Earlier alone, you told us that QU was C and C, Q and Q plus capital B,
And
weight,
yes,
and gamma.
So you are confused between the B. Yes, I mean you are confused between the B and the
One is
uh,
the capital B and the
the small b. Yeah. So I know. So don't worry. They mean the same thing. You get it? Hello. I want to make sure you understand. They mean the same thing. The B is the breadth of the foundation. Depending, some people can refer to it with the small b or capital B. It doesn't matter. It means the same thing. Okay. Yes, means the same thing. So actually you should have started by answering. So C and C plus, please, I need you to, because you need to learn, I need you to hear you people saying it. C and C plus
Q and Q.
Q and Q.
Then I have small b and f.
I have small or capital B, it doesn't matter. Gamma, you forgot gamma one and gamma, not F, that's and gamma, okay? So the only thing you will struggle how to find, which we are not going to show you in this class, is, and actually it's not difficult anyway. NC here now is, okay, first we need to calculate NQ. The gamma here is what? Gamma is 20. So you need to spend some time here. So you substitute 20 there, 20 some formula there, 20 pi. Please remember the angles. Okay, no, it doesn't matter. So 20, just substitute pi 20. You can solve this, right? I need to get some formulation, some confirmation. You can solve this, right? Yeah, I need some answer. You can solve this from this formula, putting phi equals 20. Not try, this is just a substitution. Okay, you do it. If there's a problem, you let me know. So in Q, then you can see based on Q, so just got alpha, okay? Then you can find MC here, MC is there, and so that's all. No, but there is one, and gamma, and gamma you can also, and gamma, so you can see MC and then gamma are based on NQ as well. So so this one you can get. So this is the difficult part, the formulas. But in fact, this NC and Q and gamma, there's a table you can check. But this is the first part, so you need to do the difficult part first. So NQ and gamma, all right. So C, you know, C is 500 here, right? 500. Q I have told you, so DF there is 5 feet, so Q would be, someone give me formula for Q, just to make sure we are communicating. You know, sometimes I might assume we are communicating, but I'm speaking to myself. So please someone, how to, the actual figures, how to calculate Q. Please. Hello? Class rep or Patrick or whoever, anyone else.
Gamma DF.
No, I need the, yeah, that's okay, but gamma, now they suggest substitute the values directly. Gamma DF, gamma is how much? Hello?
That we tend to confuse these units because we are seeing PCF, we are seeing fits.
That's okay.
Are you seeing?
That's okay. Just wait. Let's wait. Let's use them the way they are first. So this is 125 times 5, right? Isn't it?
Yes, sir.
And then the B here is 6. Gamma is 5. Gamma is 125, and gamma you will have calculated. So these ones have some so this is first the upper bound solution. So you need to do two things: the lower bound solution. So this is the upper bound solution, the lower bound solution. The answer is here for you, and Q, in fact, is calculated already, and Q. But please make sure you can get these values, alright? And Q, and C, and gamma. So the upper bound solution is this. The lower bound solution is that. Yeah. So I need to make sure you're very clear on what to do, and after this class stops, make sure you are able to get those values, and if there's a problem, you make sure I clarify the next class so that it's very clear exactly what we are talking about. Is that okay?
Yes, sir.
So please remember these values, and tomorrow I'll give you a table. You don't actually, normally you don't need to calculate using the formulas. You just have a table where you can check them. But because you learn by doing the hard work first, you have to do the hard work first. And tomorrow I'll give you a table where you just read. You don't need the calculation. So, and then that's the first thing. Number two, someone said the units are confusing, and I did that intentionally for this reason. So you do it in this these are English, I don't know, American units first, and then convert. You get it? Because most students have noticed don't even know how to convert. So find a conversion and use standard units, kilonewton per meter squared. Okay. 1 feet is about I think 0. You find out for yourself. So 5 feet is about I think 1.5, 1.6 meters there. Is that okay? 6 feet is about 2 meters. So you calculate for yourself. How to calculate pound per square? That's pounds per foot. PCF is pounds per foot. Pounds per foot, yes. Pounds per cubic foot. PCF is pounds per cubic foot, please. And then PFF is pounds per square feet. So you convert that into, that's the point you need to learn, such that when you go out there you can convert. So do it using the English unit. These are okay, the American or the English units. After you finish that, actually that part is already done for you. You go convert them into kilonewton per meter. So if you don't want to confuse yourself, just redraw this diagram and convert everything into kilonewton per meter. And I just demonstrate to you, it's easy in fact. Of course, for the purpose of exam, you need to remember 1 feet is how many meters. But for the exercise, you can use the internet. I think the internet is your friend, not your enemy. So you go to the internet. Okay, Google. So convert